Okay, now we're getting into the good stuff. We're actually going to take our recursion and start seeing how it relates to our equations of lines. Okay, so first of all, let's just grab an example. This is kind of like one of our time-distance relationships. So let's write our recursive routine. So the start of this guy is 12. So start is 12. And our rule is, well, let's see, it's going up 5, then it's going up 5. So it keeps going up 5 each time. So our rule is plus 5. Okay. Well, what we can use for an equation of a line is this right here. So first of all, a linear equation is just a straight line, right? Linear, it's got the word line in it, makes a straight line. And I'm sure a lot of you might even be familiar with y equals mx plus b. So that's great. If you got that down already, you're going to be ahead of the game. If you don't know what y equals mx plus b is, don't worry, we'll get there in just a little while. Right now, let's just deal with this. We're going to write a linear equation as y equals the start plus the change times the x. Or really, when I say change, it's our rule for our recursion, how it's changing. Okay, so for example, let's go back to this last slide. If I wanted to write a linear equation for this, I would say y equals the start, which is 12, and then I would put the change, the rule. So plus 5 times x. So here is the start that goes first, and then we put the rule or the change as the coefficient on x, the number in front of the x. Okay, and we'll talk in a few sections on what those actually mean on a graph, but we're just thinking about start plus change x. That's what we want to get down, start plus change x. Your book is going to call this intercept form, which is the exact same thing as slope intercept form, which we'll get to in a little while, and that's our y equals mx plus b. So if you're not familiar with that, like I said, don't worry. Okay, all it is a is like the start, or in this case on a line, it's the y-intercept. Whereas in slope-intercept form, that's our b. Okay, so it's just using a different letter. And then in intercept form, they use b for the slope, or what they say, the coefficient of x. So b is the slope in this case, whereas in y equals mx plus b, the m is the slope. But what we want to remember is that the start is by itself, and the change, or the slope, or the rule goes in front of the x. That's what we need to get down. So if I go back and look at this last example, this equation could be written just like this, which is intercept form, or our, like start plus change x, or it could be written in slope-intercept form, and all that happens is these two guys just flip-flop spots. We just say y equals 5x plus 12. And I'm guessing more of you are familiar with that way to write an equation than the green one. Okay, but either one, they mean the exact same thing. I'm going to write all mine as start plus change x, though, for today. All right, so let's take an example. Let's look at the recursion for it, and then we'll build into our equation. So it says Marissa's workout. By jogging to the gym, Marissa burns 215 calories. Her workout at the gym on a stationary bike burns 3.8 calories per minute. Write a recursive routine. Well, I got a nice table here. Right, my start is 215 because she burns those 215 calories riding the bike. And our rule is what? It's going up. What, 3.8 each time? Oops. It told us that. So our rule is plus 3.8. Well, can I write any equation for that? Yeah. So we can go y equals, remember, start plus change x. Change times x. Well, our start is 215, and our change is 3.8, so 3.8 times x. So there's our equation. And if you haven't flip-flopped, that's totally fine. Y equals 3.8x plus 215. So now let's take that equation, that y equals 215 plus 3.8x, and let's compare it with if she just worked out at the gym. So if she just worked out at the gym and didn't run at all, if she didn't jog to the gym, what would her equation be? What would be missing out of this equation? Yeah, the 215 would be gone because she didn't run. So it would just be y equals 3.8x. Okay? Well, let's use our graphing calculators. Let's bust them out here, and let's go ahead and graph these guys. Let's start learning how to graph on these calculators. So on our calculator, we have what we call the equation editor. Our equation editor is y equals, right? Because that's what all of our equations are, y equals. So I'm going to click on the equation editor. And all these plots should be turned off, so make sure those are turned off. If there's a dark spot on them, you just have to go up and hit enter to turn it off. And make sure all these are cleared out. So let's go ahead and type this in. So I got y equals, well, I'm going to type in my first equation, 215 plus 3.8x. So 215 plus 3.8x. Well, the x is a variable embedded into our calculator, so there's an actual button for this. If you notice right here, this is what we call, it's like our variable button. We have x, t, theta, and n. This is what we want to hit anytime we want to use an x for an equation of a line. So I'm going to hit that. And then I'm also going to graph my other one, y equals 3.8x. So 3.8, and then get that x. Okay. And then to graph it, we just go over and hit, oh, nothing showed up when I hit graph. Well, that's not so good. So what do we have to do? Well, sometimes I might just go to zoom, and then we have a lot of different options, okay? Zoom standard is a very popular option. Okay, if I zoom standard, it's going to make my x-axis from -10 to 10 and my y-axis from -10 to 10. So I'm going to go ahead and do that. I'm going to go down to zoom standard, just try to get a very generic graph, and I'll hit enter, and let's see if it shows up now. Okay, I got one of the equations. Which one of these equations do you think it is? If we take a look here, well, if you're familiar with your slope-intercept form, you would notice that my green equation does not have a y-intercept. So that means my y-intercept is 0. So this would be the green equation, where this y-intercept is 215. So I need this equation to appear. Well, in order to get them both to appear, there's another zoom option we can try. Okay, and this is called zoom fit. So we got to go all the way down to 10, zoom fit. There we go. So now your screen will actually fit both equations. And if you're still having trouble, that's when you can adjust your window. And your window, we'll have to work with this as we go, but this is your x-axis from -10 to 10. X scale, it's counting by ones right now, so you'll notice there's 10 dashes on each side for a total of 20 dashes. Y min they put as -38. The Y max was 253. Why do you think it went up to 253? Well, it's got to be at least 215, right? Because that's the y-intercept here. Plus, it's going up 3.8 each time, so it needs, something a little bit higher than that. And they're counting by ones. We probably would want to count by something bigger than 1, because that's a lot of tick marks. I might even count by 20s. There we go. And I'm going to go back to my graph. Okay, so if you take a look, what do we notice about these graphs? Well, the red one, right, the one where she actually runs, she's starting out by burning a lot more calories. And if I take a look, I could go up and take a look. I could scroll up there. If I hit trace, it actually is going to put a dot right on my line. See, so I'm on my first equation, 215 plus 3.8x, it tells you. And I can scroll right and left to see, like if I went over to here. Let's just move over right here. X is 4. What does that mean, X is 4? Well, that means 4 minutes, right? That's what the X represents here. So in 4 minutes, she's burning 230 calories. So I can use this to help me find some things, right? If I hit down, it's going to go to my other equation, right, my 3.8x, and I can do the same thing. So if she doesn't jog to the gym, in 4 minutes, she's only burning 15 calories. Okay, so just some things to compare by using our calculator there. So if Marissa works out for 45 minutes, how many calories will she burn? And let's do this when she's jogging. Well, if I have my equation, where would I plug this 45 into? Well, let's think this 3.8 represents 3.8 calories per minute, right? And what do you think this y would represent? Yeah, that would be our total calories burned. So the 45 minutes, that's got to be for x. X must represent our minutes. So I need to plug that in for x. So I'll take 215 plus 3.8 times 45. And what does that get us when we type it in a calculator? Looks like 386 calories. Make sure we have a label. All right, so how about this? If Marissa wants to burn a total of 329 calories, how many minutes does she need to work out? Well, we just talked about what represents total calories. The y. So we need to plug in 329 for y now. So 329 equals 215 plus 3.8x. And so this is why we need to be good at solving our equations, because we need to get the x by itself. Well, can I divide by 3.8 yet? No, I need to get rid of the 215. Remember, because we're working our PEMDAS backwards. So the inverse of a positive 215 is a negative 215, so I'm going to subtract 215 from both sides. And we're left with 114 equals 3.8x. And now 3.8 times x, the inverse is dividing by 3.8 since we're multiplying by it. Whatever I do to one side, I do to the other. So x would equal 30 minutes. And there we go. Very nice. What else can we do here? Well, we can use our recursion and write equations. We've already learned that. So let's just get a couple of just easy, nice practices of this. So let's write a linear equation for each recursion. So here's our start at -5, and here's our rule adding 4. So we'd say y equals start plus change x. So plus the rule times x. Y equals -5 plus 4x. Or remember, we can always write it as 4x minus 5. I could flip-flop these guys as well. Just remember, keep the sign that's in front, right? So that's a -5. That's a positive 4x. It's the same thing. Positive 4x, -5 if I would flip-flop. I'm okay either way. You can write it either way. And let's just do one more. So 3 is our start, so y equals start plus change x. So I can say plus negative, or I might just say minus 7x. That's just fine. You don't have to put plus negative. They're the exact same thing, right? Y equals 3 plus negative is the exact same thing. Okay, so either one's fine. And let's do one other situation without time distance and using some different variables, because you can. It doesn't have to be y and x, but we usually like that so we can graph it. So in this case, Joy makes mittens from wool sweaters. This equation, m equals 23.7d, can be used to model the number of mittens made, where m is the number of mittens and d is the number of days. Let's just talk about what everything means here. So first of all, what is the real world meaning of this 23? Well, that 23 is our start. So what does that mean? 23 what? So let's just break this down. So D stands for number of days. 7 would mean, we'll get there. M is the total amount of mittens, right? So M is the total mittens. So 23 has to do something with mittens. So 23 would be how many mittens we started with, right? The start. So 23 is the number of mittens we started with. Or when no days have gone by, we had 23 mittens in the beginning, or something along those lines, okay? So then that 7 must mean we're producing, well, D stands for days, so 7 times D, we're producing 7 mittens a day. So 7 mittens made a day. Or 7 mittens produced per day. Don't just say 7 mittens, it's 7 mittens per day, right? Because we're multiplying by the D. So D equals 10. What does that represent? Well, that represents 10 days. And could I calculate how many mittens were made in 10 days? Sure, I could use my equation. M equals 23 plus 7 times the number of days, which is 10, and I would solve from there. What about when M equals 58? What does that mean? Well, that means 58, what M is the number of mittens, our total mittens. So 58 represents the number of mittens. And I could plug that in and solve if I wanted to for the days. I could put in 58 for M and say 23 equals, or plus, I could say 58 equals 23 plus 7 times D, and I could solve for D to see how many days it would take to make 58 mittens, okay? So using our y equals start plus change x can help us solve real-world situations, whether we use it to graph or we use letters like M and D rather than Y and X. It doesn't really matter.